These examples go with lesson 8.2, hypothesis tests for a population mean, standard deviation known. This is part 4 of 4. Example 18. You want to test the null hypothesis mu is equal to 4 versus the alternate hypothesis mu is not equal to 4, so you can compute a 95% confidence interval for mu. The 95% confidence interval is 5.1 is less than mu, which is less than 7.2. Part A, do you reject the null hypothesis at the alpha equals 0.05 level? Well, let's see. What we're really looking for is, does 4 fall within our interval here? 4 is actually less than 5.1, so it's going to be to the left of our interval, and it's not going to be included inside our confidence interval here. So because it's not in the confidence interval, then we are going to reject the null hypothesis. Part B, your friend thinks that alpha equals 0.01 is a more appropriate significance level. Can you tell from the confidence interval whether to reject at this level? All right, changing the significance level is going to increase the confidence interval here. So it's actually going to go a little bit lower than 5.1, and it's going to expand out further than 7.2. But we don't know exactly how far. So what's going to drive this to actually widen is the fact that our alpha value here is going to change the critical value that we pull out of table A3, and that is actually going to increase the margin of error, and the margin of error, when it increases, is actually going to go further to the left and further to the right from the actual mean. So we can't tell for sure at this point how much 0.01 is going to expand my confidence level. It may go enough to include the 4 in it, but we're not sure. So the answer to this question is no, we actually do not have enough information. Example 19, a hypothesis test is performed at a significance level alpha is equal to 0.05. What is the probability of a type 1 error? Well, to answer this question, let's go back one slide. All right, this slide is all about the alpha value and the probability error. And what we're interested in is this part right here. When a test is performed with a significance level alpha, the probability of a type 1 error is alpha. So in example 19, if our alpha level is 0.05, what is the probability of making a type 1 error? That probability is 0.05. It is our alpha level. Example 20. Charlie will perform a hypothesis test at the alpha equals 0.05 level. Felice will perform the same test at the alpha equals 0.01 level. Part A. If the null hypothesis is true, who has a greater probability of making a type 1 error? Well, remember, the probability of making a type 1 error is the alpha level. So Charlie's alpha level for his test is 0.05, and Felice's probability of a type 1 error for her test is 0.01. So question A is really asking me which one is greater, 0.05 or 0.01, and the 0.05 is greater. So Charlie actually is going to have a greater probability of making a type 1 error. Part B, if the null hypothesis is false, who has the greater probability of making a type 2 error? Well, if Charlie's got the greater probability of making a type 1 error, then Felice must have the greater probability of making a type 2 error. Example 21. A test was made of the hypothesis, the null hypothesis mu is equal to 15 versus the alternate hypothesis mu is greater than 15. 4 statisticians wrote summaries of the results. For each summary, state whether it contains enough information. If there's not enough information, indicate what needs to be added. Part A. This is the first statistician. The p-value was 0.02, so we reject the null hypothesis at the alpha equals 0.05 level. This one's okay. We want to be sure and include our p-value so that other people who are reading over our experiment can see what p-value we use to compare when we were trying to decide if we were going to reject the null hypothesis or not. So it's a good idea to have the p-value in there. All right, part B. The critical value was 1.645 because Z is greater than 1.645. We reject the null hypothesis at the 0.05 level. Okay, this one is actually missing something. We would love for them to include the Z statistic, whatever it's going to be. So the 1.645, that came out of our table A2 or the table A3 there. And we need to see what this is right here to see the comparison between the two of them. So this one needs to include the Z statistic. All right, part C. The critical value was 1.645. Because Z equals 2.05, we reject the null hypothesis at the alpha equals 0.05 level. This one's okay. It includes our critical value in here, tells us what our Z statistic was, and the alpha level that we used. So this one's good. Part D. Because P is less than 0.05, we reject the null hypothesis at the alpha equals 0.05 level. This one, we are actually missing this number right here, the p-value. It would have been better to include the p-value inside this statement so that we could see that the p-value that was calculated actually is less than the alpha value that was used. So this one we want to include the p-value. Okay, example 22 here kind of illustrates the difference between statistically significant and practically significant. So something that is statistically significant happens when we reject the null hypothesis, but practically significant means kind of what it says. In practice or in practicality, I mean, is it really a significant finding? So you kind of have to interpret your results in the context of the question that you're trying to answer. Okay, a certain type of calculator battery has a mean lifetime of 100 hours and a standard deviation of sigma equals 10 hours. A company has developed a new battery and claims it has a longer mean life. A random sample of 1,000 batteries is tested and their sample mean lifetime is x bar is equal to 101 hours. A test was made of the hypothesis, the null hypothesis mu is equal to 100 hours versus the alternate hypothesis mu is greater than 100 hours. And for part A, we're going to show that the null hypothesis is rejected at the 0.05 level. All right, let's come up here and let's figure out what our standard error is going to be, because we need that in order to find our test statistic Z. Now the standard error is going to be the standard deviation for the population divided by the square root of our sample size. So in our case, we're looking at 10 divided by, let's see, 1,000, because we've got 1,000 batteries. So 10 divided by the square root of 1,000. All right, let's put that in the calculator and see what we get. And this is giving me 0.3162. Okay, to get our test statistic, Z, we are going to take the mean, which they gave me to be 101, and we are going to subtract mu0, which we can find right here in our null hypothesis, so that's going to be 100. And then we're going to divide that by the standard error that we just found, 0.3162. All right, and let's put this in the calculator and see what we get. And if we round this to 2 decimal places, this is giving me 3.16. All right, let's see if we can take a look at the picture of what's going on here. We are doing a right-tailed test, and we know that because of that right there. And I am actually going to do a critical value test on this instead of a p-value, okay? So I am going to be looking for this right here, this value right here, so that all of this area to the right, because we're doing a right-tailed test, is actually equal to 0.05. And what I'm going to need to do is pull up table A3 to figure that one out. All right, so when I get onto table A3 and I look down at the Z line under the 0.05, I see that this value right here is 1.645. Okay. Now we're going to compare our test statistic to the critical value that we found. Where does 3.16 fall? Is it over here in the white unshaded area, or will it fall back here in the rainbow shaded area? In other words, is 3.16 more than 1.645, or is it less than it? And I think we can all agree it's going to be way back here somewhere, much bigger than the 1.645 critical value that we found. And since it falls within our shaded area, we know that we're going to reject the null hypothesis. So we're going to reject our null hypothesis because 3.16, our test statistic, is greater than 1.645, our critical value. All right, part B, the battery manufacturer says that because the evidence is strong that the mean is greater than 100, you should be willing to pay a much higher price for its battery than for the old type of battery. Do you agree? Why or why not? Now, this is, of course, an opinion question about whether you agree or not, but I can tell you my feelings on this. The old battery gave us a lifetime of 100 hours, and the new battery definitely gives us more hours. I mean, this is some pretty strong information right here. But if you'll take a look, when they took the mean in a sample, the mean was 101, and so I'm actually only getting about 1 hour more use out of this battery than I was before. And in my opinion, I don't think paying a much higher price for 1 extra hour's worth of battery power is really going to be worth it. So my opinion would be no. This is not practically significant because it's only going to be for 1 hour. And we can say no because 1 hour is not considered to be practically significant.